All right, so let's get rolling. So, hopefully everybody online can hear me. I'm also recording. Everybody has a chair in here. Okay, so your chair's not working?
It's broken already.
Oh, well, we got some backups up here. What kind of chair you got? Oh, well, I got one of those. I could switch to this one. Like, do you want to switch now? Oh, here, I'll just. I'm about to toss this over here. All right. I'm the back surgery guy. You're like, doing this crap?
Yeah. Have the wheel too.
It wasn't broken back before, it's really broken now. All right. All right, is that better?
Yeah.
Or did I compress it down too much? All right, so remember, online people, if you log into Zoom using your Concordia credentials, clicking on that SSO login, you won't need me to admit you and you won't get stuck in the waiting room. Some other housekeeping things. My next back surgery is 8 a.m. Friday. The class is until 11. So we should plan on having class on Zoom. And hopefully I've come out of anesthesia enough to code. Any way you cut it, we should have a good day. Yeah, they got to put me completely out for this one. And I have the same one on the left side a week from Friday. So the next 2 Fridays will be on Zoom. I got to be there like at 6. So the surgery's at 8. I'm guessing it'll be done by 8:30. They bring me I should be out on the road by 10. We can have class at 11. We're good. Not to screw with me though. See how with it I am. And the theory is this should be the last surgeries for a while. These are the big ones we've been working up to. Okay, so this is coding 2, right? All right, just like last semester, 30% of your grade is homework. All the programming assignments should be submitted with the self-assessment thing. That's all up there on Blackboard. Blackboard should be all set up. Over on the left, I have the self-assessment template. I have the syllabus up there. I have links to a bunch of different things we're going to be using this semester up there. Whatever. There'll be a midterm around week 8. There'll be a final during final exams week. Exams worth 70% of your grade. Remember, I have the same policy for those of you who are new in this class. If you transferred in or whatever, my policy is if you do better on the final exam than you did on the midterm, I'll replace whatever you got on the midterm with what you got on the final exam. Okay, so you can get a 0 on the midterm, presumably, and still get an A in the class. Okay, so my job is to give you a grade based on how well you've mastered the material by the end of the semester, and I give you as many opportunities as possible to do that. I like to view homework as kind of practice for the big game. I tend to grade homework pretty easily, so it would be in your best interest to work hard on it, but always turn it in even if it's not working. Okay, I tend not to penalize you very much. Think of it like if you're on a basketball team, if you work really, really hard at practice, even if you're the slowest person on the team, even if you can't make a free throw, whatever it is, I'm going to judge you mostly based on how you perform in the games, with my final assessment being how did you perform in the final? Okay, the championship game. Championship game can make up for a bad performance on the regional qualifier. These are things I think. All right, so questions about that? There will be plenty of homework. I give assignments. There'll be at least 1 assignment per week. Sometimes there'll be 2, sometimes there'll be 8. Sometimes I'll give you an assignment, but not give you enough stuff to do the assignment. Those are always fun ones. So, all right. So, what are we going to be working on this semester? So we're going to be starting with two different things. So we're going to start off continuing on with Java. We're not going to be doing this for very long. We're going to be working on Java for probably a couple of weeks. And then we're going to be moving on to Unity Game Engine. All right. So really what I'm going to use Java for, at the end of last term, we were writing our dungeon. Remember our dungeon crawler? Here, I can bring up the slides. Here's our dungeon crawler. Okay, remember we had our dungeon with exits and rooms and all this stuff. And did we actually end up writing that in Java in the end? We had it in Java in the end. Okay. So we have that in Java. So we'll dive back into to that code. And really the thing I want to talk about to kind of finish that off in this course is something called threads. Anybody heard of threads before or heard of multi-threading? All right, so let's talk about these guys, because this is going to give us a foundation for going into the Unity Game Engine. Because what we're going to do is when we go over to Unity Game Engine, we are going to recreate our dungeon crawler as a video game. Okay, so you're going to have obviously 4K high-end graphics. Not the way I'm going to make it. I'm going to have boxes. That's what we're going to have. Okay, but you'll be using a game engine. This is the same tool that they use to make your Xbox games, your PlayStation games, virtual reality games. So this is the core physics engine that they use to make all sorts of games. The two competitor engines are Unity and Unreal Engine. At any given point in time, one of them is better or worse than the other one. Think of it like iOS versus Android. Okay. The reason we mostly use Unity is it has significantly better documentation and many more examples out there. Okay. You might find, long-time game programmers who might say, oh, well, Unreal's better at this. It has better particle effects or this, that, and the next thing. It's much harder to find examples and things like that that might help you in working on stuff. At the end of the day, though, once you know how to use one of them, the learning curve to get to the other one is pretty minor. No different if you ever had an iPhone and switched to Android or the other way around. You spend a couple of days kind of figuring out the quirks, but they're basically the same thing at the end of the day, right? All right. So, and the other reason we use, well, I guess this isn't necessarily a reason. Unity also uses C# as its scripting language, and C# is basically the same as Java. So one of the very first things we're going to do is we're going to convert all of our objects that we've written for our dungeon crawler into, so they're all Java objects right now. We'll convert them into their C# equivalents. And you're going to see how few things we need to change. Almost always it's like, well, in Java, string is capitalized, where in C# it's lowercase s. Stuff like that. Okay, so it's they're extremely, at worst, they're first cousins. Frankly, they're probably brothers or something like that. All right, now let's go back in time a little bit before we talk about threads and talk about the predecessor of threads. And this actually comes full circle. If you remember early on in the last semester in 200, we talked about kind of the history of our operating systems. And you're like, well, why are we talking about this in a coding class? Yada, yada, yada. Well, now you're going to kind of see the loop. Now, I'm guessing for this class is the oldest operating system you use, Windows XP. How many of you use Windows 98? How many use Windows? What was the oldest operating system? Windows 8?
I use Windows 10.
Windows, oh my gosh. Anybody use Windows 7, Windows 8, Windows 10? So you're still using the first operating system you started using?
Oh, no.
Oh. So, and this, so actually this is good because it's even more poignant for this group. And hopefully we'll show another one of my points. Remember when I told you the bad news of why I use C++, right? Why did I say we chose to use C++ in the first class rather than a more modern language? What's the advantage of C++? Shows you what's going on under the hood. And maybe I use an example early on in the term about, way back in the old days of the original time when they first came out with cars, you have to get out and kind of crank the engine to get it started, similar to like manual lawnmowers where you got to pull the ripcord, right? And then when I never had a car like that, but when I had a kid, you had to you got into the car, you always had to press the gas a couple times to prime the engine before you could turn it on. You had to get a little fuel in there. Similar if you're a boater now and you have a little bit of a, not actually that old of a boat, but you have the little squeeze ball thing that squeezes some fuel in there. The equivalent, same thing. you gotta put a little fuel in there so when you turn it on, it has something to blow up to get the engine running. All right. But now when you get in your car, modern day cars, what do? You just turn it on, right? Or you push a button, right? Some of them have buttons now. So things like that, which maybe these aren't huge deals, but how many of you would, especially we're supposed to get like a foot of snow tomorrow, how many of you would want to go outside and have to crank the engine manually I mean, not that you should go anywhere with a foot of snow on the ground, but that would not make you happy, right? All right. So how many of you have cars that have auto starters where you can just push a button from inside the house to get it nice and toasty before you even walk out there? Oh, isn't that good? Man, I'll do that just to like melt the snow. I don't even want to like scrape it off my windshield. I'll just start the car an hour before I go out there and just let it melt off. So although I've been in the Caribbean for a month, and so I came home and my wife parks her car in the garage. So I have my car out in the driveway. So I don't know, like that thick of basically iced snow on my car. So I tried to melt it off, but a while I had to get out there with the thing. I was upset. So I only did half the windshield and just hope the rest slides off on the way to the school. All right. So in any case, we appreciate some of these things, right? And we can better appreciate things when it used to be different, right? When I was a kid, we had the corded telephone where you had to do the circular thing and you get the callus on your finger where you hit. Okay. And most of you only seen that in a museum, right? And it's not like I'm that old, right? But I've been around longer than you have. Okay. I'm 46 this month. So remember, birthday's January 27th. There should be a party and flags and all sorts of, a lot of bowing, probably. But so the world has, I mean, if you think about the number of things that have changed in the world just in the last 20 years since your lifetimes, right? And the internet always existed for you, right? Since day one. I used to have to ride my bike over to my friend's house to see if he wanted to come out and play. There was no text messaging and stuff like that. And if my mom was on the phone with her mom or something, I couldn't make a phone call to him because we had dial tones, busy signals. But it was even worse years before that, where you have to talk to the person to connect you, like, yeah, connect me to mom. And they connect a couple of things up. Okay, so in any case, we use a language like C++ to, at the very least, help us gain an appreciation for how things used to work. And so even if we took it to a little bit more modern, anybody in here have the very first iPhone? So I'll use this example from the very first iPhone. So everybody in here probably has a smartphone of some kind now. You can listen to music on your phone or something like that. So we go back to the original iPhone, which was groundbreaking, and in terms of the things it can do, it allowed you to actually browse the web for like real on your phone. There was, smartphones before that, like BlackBerry, and Microsoft had some stuff where it was a pretty janky browser. You didn't do real stuff on it. You had to be like under duress to use it. But in that very first iPhone, what people we take it for granted today. Very first iPhone didn't have an app store, first of all. So the apps that came with the phone were what you had. So you had YouTube. YouTube used to be this gold colored logo thing for the thing. So YouTube came with it. Then they got kicked off later because Apple doesn't like Google, but they had an app yet. Yeah, Google Maps was on there until they got kicked off because Apple had their own maps. But there was no app store. There wasn't the ability for software developers like us to start writing software and release it out there without having to. I mean, back then, if you wanted to write software, you had to go through a publishing company to get it up on the shelf at Best Buy. Best Buy used to have a gigantic software section. I remember camping out at a store called Babbage's in the mall in Champaign, Illinois, to get my copy of Windows 95. They were scarce, and it was like a 27 floppy disk install. So, so you picked the thing, it was like a brick. It's like, please enter disk 13. You walk away for an hour, come back. It was, yeah, those were the days. So in any case, first iPhone didn't have an app store, whatever. Okay, fine, but it had stuff on it that, you know, you could do your email, which that's something we do on our phones, right? Browse the web, YouTube, some music. Really, if you had just those four things, you could probably survive. You might complain a little, but when you consider what it was like before that, you would have survived. But an interesting thing that is little known today is that if you wanted to check your email on your iPhone, you had to stop listening to your music. Couldn't do two things at once. You had to listen to your music or check your email, one of the two, right? Because when you switched away from an app, the app that you just put in the background went to sleep, okay? Because the device did not support multitasking. If you, now Android really didn't come out till about 1.5 years later or so. And day one of Android had multitasking. Is that better? Way worse. Why? So this is where you think through things and decide, well, just because something sounds better doesn't mean that its implementation was actually better. So with the success of iPhone, because remember, Apple had never made phones before. So when Apple first was coming on the market, they were exclusively available with AT&T. Now they went to Verizon first. Verizon turned them down. Said, Apple, there used to be a flop. So for a long time, you had to be an AT&T customer to have an iPhone. So imagine how quickly iPhone got popular. AT&T picked up a lot of people during that period of time. And then there was a revolution. So they eventually got onto all the other carriers. But in any case, there was a big race. So the iPhone got very popular. So Google was in a situation where it needed to kind of rush to market getting Android. And iPhone is built on top of a Unix-based operating system. Android is based on top of a Unix-based operating system. But here's the difference. iOS, the operating system that the iPhone runs, was built specifically for a smartphones in mind. And one of the design decisions they had to make was, we're only going to allow one application to run at a time, rather than you have a whole bunch of applications running in the background. Because if they're running in the background, what are they doing? Burning your battery life. So day one, Android comes out, and it's based on the desktop multitasking model of Android, of Linux. So day one, you can listen to your music, you could check your email, blah, blah, blah. And you had battery life that lasted like 20 minutes. Okay. There was all these jokes on TV, people carrying around car batteries to power their things. On the early app, I mean, keep in mind, the app stores didn't become popular for a couple of years. So this is several years into Android. This is not like year one only. The most popular apps on the App Store were what in the early days of Android's App Store? Anybody know? Apps to close other apps. So you had an app where at a push of a button, you can kill off all your background apps that were draining your battery. Those were the popular apps to keep your battery life up by making sure you didn't have an app that you opened 3 weeks ago still taking up battery space and CPU time in the background. All right, so you understand that, yeah, if you have a computer that's plugged to the wall, having your stuff, you know, running in the background, using up some system memory, stuff like that, like even we look up here. So this shows me my current available RAM on my computer, 47.29 gigabytes. All right, this computer has 96 gigabytes of RAM. So I'm using half my computer's RAM. Who knows what it's even being used for, but I got plenty of RAM left over, so who cares? All right, so here, significant uses, Zoom, and it's probably the recording for Zoom is using a lot, but whatever. I have enough memory and I actually am running off a battery, but whatever, you get it. It's less of a problem on machines like this because I can put bigger batteries in them. I don't have to worry about the use of those resources. I got plenty of extra. So I don't have to go and close down programs that are running in the background. All right, so this idea of multitasking, having more than one application running at the same time, was something that was available on Android day one, was not available on iOS until actually several years later. They had kind of a hybrid approach a couple years later, but not true multitasking. And from day one, all the Android commercials would brag about how, you had the multitasking ability and things like that. Battery life was crap. Wasn't even close to the same experience. Similarly, how many of you are familiar with a technology called Flash? Okay, so Flash, whenever you go to a web page that has stuff moving around on it years ago, like if you went to like use the poker games like on Yahoo Games or something like that, those were all Flash-based games. Okay, Flash was made by Adobe. And super popular. Basically, anything on the web that was interactable on a web page, like a video game looking thing, was written in Flash. So, Flash was super popular. And so in the early days, Android also had mobile Flash. Now, before I even talk about that, keep in mind, Flash has now died, thanks to Apple. Apple put the line in the sand and said, we're never going to support Flash. So all the new stuff, whenever you have an online game type thing, it's written in HTML5 now. Okay. Apple is the reason HTML5 became a reality. They didn't make HTML5, but with the iPad and the iPhone, if you wanted to have stuff that used to be Flash-based work on those devices, you had to convert them to HTML5. Okay. Now, this was the catch. You talk to an Android person, they always had that little card in their pocket. They would say, oh, here's the reason we're better. Right? And keep in mind, I've run both. I like Android. Actually, there's features of Android I probably prefer to iPhone, but whatever. One of the things would be, oh, we have Flash support. Well, years later, I would ask a class, this is back when people still knew what Flash was and stuff like that. But I would ask them, how many of you appreciate the fact that you have Flash support on your Android device? And a bunch of people would raise their hand. And the punchline was Google had quietly removed Flash support like 3 years before that. Because you thought that running programs in the background was bad on your battery. Flash, you might as well just started with 1% battery life. And you could see it even on laptops back then. The Flash program was written years and years before, and it was a great program, but it was never written to be running on a computer that running off a battery. So if you even opened it up on a laptop and you just went to some web page that had a little Flash thing running on it, a laptop that was supposed to get, call it 4 hours of battery life back then, would get like 20 minutes. Because Flash was just very, very, very process intensive. And the kicker was on those smaller smartphones, it never worked well. Any page that had Flash on it, it was meant to be kind of a full screen gaming looking thing. It never made sense for a smartphone anyway. So you would try to do something that was Flash based on a smartphone. It was a bad experience regardless, and your battery was dead 5 minutes later. All right, so then HTML5 took over, yada, yada, yada. But punchline with all this is that just because something sounds like it's better because you're used to having that ability somewhere else doesn't necessarily mean that it's what you want. Make some sense? Years later, Apple came out with their solution to multitasking. Really, their solution to allow you to listen to music and check your email at the same time. And what they let programmers do, the App Store had already been out for a while at this point, is they allowed programmers to hook into like 8 different subsystems of the operating system. Things that your app might want to do when it's in the background. All right, only those things. You couldn't just have it do anything you wanted in the background. But one of the things you could do is you can have it continue playing music. You can hook into iOS's music playing capabilities, and basically your app stayed alive like on hospice. Just it was on it was just above death, and but allowed the music to keep playing. Something along those lines. And Android kind of went along those same lines, and then they kind of evolved together. And now we have, competitive ecosystems, right? We can't come up with real examples like that today because these smartphones have been out long enough that over time they've settled into, the things that work on something that runs with a battery versus things that don't. Right. And even now, most of our smartphones allow for some aspect of multitasking in the background. Actual multitasking in the background, because now our battery technology is a lot better. So it's, we've balanced it. Okay. So in any case, this idea of having more than one thing happen at once is something we all take for granted. On our desktop operating systems, we used to only be able to do one thing at a time. You go back to Windows 3.1, can only do one thing at a time. One of the big things, and we even talked about it last semester, right? When we said, what did Windows 95 bring to the table? Besides the start menu, the new nice user interface, yada, 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 it brought multitasking, allowing you to do more than one thing at once, allowing you to minimize Microsoft Word so you can check your email. Something along those lines. All right. In order to do that, we needed the ability to do something called multiple processing. So multi-processing. Having more than one program running at once. A program running on a modern computer is represented by something called a process. And you'll learn all about processes in CSC250, the operating systems class. You'll learn about something called a PCU, process control, or PCB, process control block. But you can think of every program you have running on your computer is a process, okay? And the way that we used to get programs allowing you to do multiple things at once was for them to create multiple copies of themselves, multiple processes. All right. So our modern day operating system, if we think about a single CPU, now all our computers have 4 or 8 cores, whatever. So if we go back to a little bit older computer that only had a single core processor, a single core processor could only do one thing at a time. Now, it would do things really, really, really fast, so it might convince us, the end user, that more than one thing was happening at once. But the reality is it was just doing things so fast that we were tricked. Make sense? And it wouldn't complete one thing at once. So basically, there's different algorithms for what's called process scheduling. This is something you'll do in the operating systems class. Multi. But in any case, so one is the generic algorithms are all your processes who want to get CPU time, wait in line. Each one gets a little bit of CPU time, then gets out of line or gets off the CPU, gets back in line. The next guy loads in. There's a cost called context switching. When you're loading on to a processor and leaving a processor, that's expensive. So you want to minimize context switching, yada, yada, yada. But in any case, that's the generic way that single core processors, generic way operating systems work today. All the things that want CPU time wait in line and they get the next available CPU time, and there's some sort of overarching maestro that decides, when something's done on the CPU versus, when it's out of resource time, something like that. So, the way, if you were a computer programmer, the way you would create the ability for your program to do more than one thing Okay, so forget about an operating system allowing you to do two things at once. What if you want your computer program to do more than one thing at once? What if you wanted to be able to ask the user for a number where on the other side, where the program is still making something happen on the screen at the same time? Those are two different things. This is blocking code, waiting for the user to enter something in. Please enter a number between 1 and 10. And then it sits there and waits for the user to type in something and press enter. Your program, your entire program is paused until that user types something in and presses enter. Whereas if you had the ability to have your program continue on doing some other things that it could do in the background while that guy is waiting, that would be nice in some circumstances, right? So we did this through something called multiprocessing. All right. Now this next section, I say this jokingly, but you need to be very careful when you're talking to people and enunciate all the words clearly. There will be a story related to this. There is remember last semester early on when we were talking about what compilers do. We talked about the compilers needed to know about two different pieces of information: the architecture, what kind of processor you're compiling for, as well as the operating system. So it could write stuff in terms of the right system calls. Remember those system calls? Well, we had a system call for when you wanted your program to split into two programs. Did you already know, or did you look it up? So we had a system call called fork. So fork would split a process into, well, let's say not split, would clone a process into a copy of itself. And then you would use an if statement to determine if you are the original, call that the parent, or the new, or the clone, call that the child. And so you have an if statement, the same lines of codes, do this, this, this. Now you get to the point where you want to do two things at once. Okay, so what you would do is you would call the fork system call. You would then, the very next line would happen. But now that would return a process ID. So you'd either get the process ID of 0 if you were the clone, or you get a process ID of some number if you were the child. I'm sorry, if you were the parent. So the parent would know about, let's think of that, the unique identifier of the child it just gave birth to, something along those lines. Okay. So you imagine having conversations with some of these words involving the fork system call and children and things like that. And imagine that you have a program that you're writing where you might want to, you have processes that are running on the computer. When you create multiple child processes, maybe when they finish doing whatever they're meant to do, you want to get rid of them. And these are just floating process IDs out there that are still being scheduled on the operating system. So maybe you'd have a program called reap that goes and reaps, like the Grim Reaper, right? Goes and reaps child processes. So imagine sitting at a restaurant at breakfast time with a bunch of system engineers having this conversation about forking processes and reaping. These old ladies were very upset. Is what it came down to. Now you've actually, I think, seen this the word fork with online GDB, where you can, when I put up a thing, you could fork that repository. You'd make a duplicate of it. So that it still hasn't gone away. We can't just call it clone or something like that, but yeah. In any case, these are the things that were there. The good news is for us, this is not the modern way of pulling it off in our programs. So we're going to talk about this a bit more, but at the very least, we don't have to worry about being overly precise with our enunciation for the entire semester. All right, because one thing that would happen with multi-processing based programs is they could cheat. And what I mean by that is I mentioned a few minutes ago that an operating system schedules the processes that want CPU time, right? And let's just use a human amount of time and say that every process gets 1 second on the CPU. That's a lot of time on a CPU. There's millions and millions and millions of instructions that can happen in 1 second on a CPU. So they would get some subset of that. But let's say that you had your program running on the CPU and it got its 1 second of time on the CPU before it had to go get back in line and wait for its next 1 second. Well, if you created a second process in your program and if you happen to have a problem you were solving that allowed you to do two things simultaneously. So for example, shoveling snow. Shoveling snow is an example of a problem that benefits from having multiple people working on it at once, right? Get 2 people shoveling snow, you can shovel twice as much snow, that kind of stuff. Let's assume you were solving some problem that did benefit from having 2 processes. Well, now when you created 2 child processes, you create a second process to do twice as much stuff. Each of those processes had a unique process ID on the operating system, which means they each got their 1 second of time on the CPU. Well, then you can have each child create another child. Now they each get 1 second. So all of a sudden, your computer program, without any oversight, could get 4 times, 8 times, 16 times the time on the CPU just by subdividing itself, assuming it could take advantage of that stuff. And this is actually how some of our early virus attacks on computers would happen. So this is where some of those numbers that you didn't like memorizing or whatever comes back to roost. Most of our, actually, it's probably up to the 2.1 billion now, but for a long time, our Linux operating systems, for example, as well as Windows, they supported up to 65,536 unique process IDs. So that means you could only have 65,536 processes with unique numbers associated with them, with the unique social security numbers, if you will, running on the computer at once. How long do you think it would take you to write a program with an infinite loop in it that just kept creating new child processes until you had 65,536 unique processes, and all of a sudden the operating system could not create more processes? Meaning that your entire computer was taken up. Let's see if I open up terminal here. So there's a program called Top that will show me the things that are getting the most CPU time right now. So here's Zoom. Here's its process ID is 7109. This is showing me somewhere in here is 54% of the CPU time, but I have a bunch of cores on here, so that's just for one of the cores. But whatever, if you had 65,536 process IDs that had already been taken, and you tried to create another program, you tried to double click on something or whatever, couldn't open it. No more process IDs available. Okay, so what would a Unix system administrator have to do if he needs to, because now the computer is basically seized up, right? No new processes can be created, and you basically have an infinite loop because this one program is just in perpetuity sitting there with infinite loops, getting its 1 second of CPU time over and over and over again with the computer doing nothing. Make sense? Well, how would you fix that? Well, maybe a Unix system administrator would go in and I'm not going to actually kill one, but here, let's say 7539. Well, here, we'll do it. 7539. What's the name of it? Create a new tab here. We'll say kill 7939. Is that right? 7539. 7539. Top is dead. So I killed that process ID. Right? I have another command called kill that lets me kill off a process I did to make sure I didn't kill off Zoom or something, mess up my recording. So I killed off my program that I started running called Top. Okay. So, oh, no problem. We just have a Unix system administrator go in and, you know, you could write a little script that gets all the current process IDs and just kills them off, right? No problem. Except there's one problem. How are you going to open the terminal if you're out of process IDs? Can't even open the program in order to kill off the running programs. So you basically had to reboot the machine, bring a whole server to its knees. So these are some of the early attacks. And there was effectively no oversight is what I'm getting at there. So you could have a computer program that just kept, you know, creating child processes over and over and over and over again, without any oversight, and just get more and more CPU time if you wanted it, which is good if you want to take over the CPU or take over the computer, but it's bad from a perspective of fairness. Okay, now, every single time you would use the system call, you would get a full-fledged brand new process with all of the, let's call it heavyweight stuff that came with a full running process on the computer. When the reality is if you need more than one thing happening at once, i.e. creating some situation where we're not blocking, we don't have code that's blocking, you don't actually need more CPU time. Because usually we have plenty of CPU time, and it's actually pretty common for programs to get their time on the CPU and not use up anywhere near as much as allotted to them. Because they're at their point where like, oh, I need to go get user input, so I need to jump off the CPU now and go do something else before I get back in line. That's common. So it's very, very common. So we really don't need to give our programs more CPU time most of the time. So that means that creating copies of processes just to get more CPU time really wasn't a great motivator. So if we had a way of creating child processes called threads that were managed by the parent process and shared in the CPU time that parent process got, we could get the benefits of having multiple processes without the consequences of multiple processes. The worst that would happen is you would hamstring the program that you were writing, where you had too many threads created, and you know, basically no work could get done because the threads, you know, you were subdividing your time on the CPU so much that nobody can get anything done. So that would be the downside, but at least it would just be your program that crashes and burns. Then you go back and readdress it and say, okay, well, maybe I don't hire 4 billion people to shovel campus. You know, maybe we get 20. We'll just call that good enough. You know, something like that. All right, make some sense? All right, so we're going to say that fork created heavyweight processes that could be a burden on the CPU/OS. Let's throw thread after that. Threads are lightweight process-like entities that share in the parent processes CPU time and, let's call it, other resources. This still allows us to write code that does not block the rest of our program from running while not taking over an OS. All right, make some sense? So we're going to call threads our modern day way of having more than one thing in our program happen at once, up to some limit, right? But more than one thing happen at once without having to, like, using that quick example of please enter a number between 1 and 10 and having to wait there for the user to do something where maybe your program over here is still cooking. Make some sense? All right. but it's done in a lightweight way where we're not asking for the operating system itself to keep track of all these floating around threads and things like that with unique IDs, because the threads are managed by their parent. Now, what gets more interesting, well, what complicates things, not for us as the programmers, but from an operating system perspective, is as our CPUs got more and more and more cores, capable of doing more and more and more actual things simultaneously, it became very common for our computers to sit there with CPUs having nothing to do. So then they had to start creating mechanisms to allow threads to get scheduled on non-busy CPUs, because the CPU was doing nothing. It's getting electricity, but it's not working, so we might as well put it to work doing something. Make sense? So we brought it right back onto the CPU, but at least it's managed by a subsystem where you can't just take over. Those threads only get CPU time if nothing else needs CPU time, that type of thing. And now we start getting into more of the operating system details of operating systems type stuff. As a programmer, what are we going to do? We're going to say, I want to spawn off a couple of threads and have 2 or 3 things happen at once. Great. All right. So let's go and look at the documentation. We're going to create some Java threads. So there's a class in Java called the thread class. And the thread class is actually a very, very, very simple class, and it implements an interface called runnable. And we talked about a couple of these things last semester, but let's just review them here in the last few minutes, and then we'll do something with them here next class. All right. So let me get down. Actually, it's up top where it says implements. Yeah. So here's a thread. A thread's only parent is the object class. All right, so it doesn't inherit from anything else other than a generic object. Okay, now when we talk about threads, there is some connection there to the operating system, right? You know, we are asking the operating system to allow our one program to kind of behave with some extra, I like to think of them as worker bees, kind of floating around doing some stuff. Okay, so there's some magic that the thread class knows how to do that it has to work through Java, which is running in a virtual machine, which is then having to negotiate with the operating system, something along those lines. So we don't need to know about the magic, but just our way of getting to that magic is through the thread class. And the thread class implements this interface called runnable. Okay, now I know we mentioned interfaces last semester, right? Anybody recall? Well, I'll just talk about it again real quick. All an interface does is it says, if you want to implement this interface, you must have these things. And the runnable interface just says you have to have a function called run. That's it. It says, look, if you want us to consider you a member of the runnable club, you got to have one of those. You know, you got to have that wristband. Right? You got to have this function called void run that, you know, does something. All right. So an interface itself isn't something that runs. An interface itself is something that says this is what's required for membership. All right. Make some sense? So the thread class implements the runnable interface, which means that the thread class will have a method called run, which it does. If I scroll down here, we'll see under methods. We have run. So here's our run method. Class method or instance method? And how do you know? We're only looking for one keyword when we're trying to determine if it's a class method or instance method. What keyword are we looking for? Static. Do you see static there? Nope. So it's an instance method. So we're going to need an instance of the thread class in order to call this method. But the trick is we never will actually directly call this method. We're going to call a different method called start. The start method, also an instance method. This guy, he contains the magic. Okay, he has the magic trick that tells the operating system how to spin up this new lightweight process to have multiple things happen at once. And what does that process do once it's born? It does whatever the run method has in it. So the run method says, do this crap as soon as this thread is born. Okay. So that means that the run method here that comes with threads by default does nothing. Doesn't have anything in it. All right. So I can create a thread, tell that thread to start, and it will do nothing. But it is a thread. Okay. So if I really want to have my threads do something special, what I can do is I can create my own class that extends thread. It gets everything that a thread is, except I can overwrite the run method, put stuff that I want it to do in there, and then call the start method, which I inherited from thread. And then poof, magically, I have a running thread. Make some sense? All right, so we'll start next class and we're going to write a thread. And then we know how to do multi-threading. So how did this projector work? Is it easier to see, worse to see? Better?
I think if we turn off the light. It's a weird class.
Okay, well, you got to figure out how to turn it off. It was all we can do to get this room gutted enough to have seats in here. This is going to be the esports practice room and classroom dual setup thing. But the delay is we have to have them fix this flooring here. You see it's all damaged by the door here. And apparently floor that they've glued down is very hard to unglue down.
It's doing its job.
I was here with Temish and he was mapping this river for robot.
Oh, cool.